In this lesson, we're going to be solving multiplication and division equations. Our goal is to use inverse operations to solve algebraic expressions using multiplication and division. We're going to be applying what we previously used on adding and subtracting in equations to multiplication and division. Let's review. An inverse operations is an operation that undoes another operation. So we know inverse operations undo each other. So in an example such as 3 minus 2 equals 1, 3 minus 2 plus 2 equals 1 plus 2, because in both cases you get 3 equals 3. So that's our inverse operations. A common mistake is that students will misinterpret inverse operations of fractions. For example, 3/4 of x equals 20 means 3/4 times what equals 20? X does not equal 15. In this mistake, students multiply 20 by 3/4, which is not what this problem is asking. So let's first start with our division property of equality. In words, dividing each side of an equation by the same non-zero number produces an equivalent equation. In algebra, a times x equals b, where a of course does not equal 0. A times x divided by a equals b divided by a. Make sure you're pausing this tutorial to write down any of this in your notes. So let's look at an algebraic expression. How do we solve a multiplication equation using inverse operations? Well, we first have to ask ourselves, what is the inverse of multiplication? Well, remember, the inverse of multiplication is division. So if we have 3 times x equals 45, so in 3x times 45, we can probably use mental math, but we're going to use the inverse operation. So what we do is we divide both sides by the same number, which has to be 3. Why is it 3 and not 45? Well, because we want to get the x all by itself. In order to do that, we have to get rid of this 3. So when 3 and 3 cancel out, we're just left with 1x, because 3 divided by 3 is 1. And 1x can just be symbolized as x. And we have 45 divided by 3, which gives us 15. So I know that 1x equals 15. How can we check to see if we're right? We just say, is 3 times 15 equal to 45? 3 groups of 15 is 45, so this checks out. That means x does in fact equal 15. Let's look at another example. We have 6y equals 42, which again means 6 times y equals 42. We want to isolate the y, so that means we're going to divide both sides by 6 so that the y will be by itself. So we divide 6 by 6, which of course gives us 1. That cancels out. So we're just left with y equals 42 divided by 6, which gives me 7. Now I need to check to see if I'm right. Is 6 times 7 equal to 42? Yes, it is. So that means my y equals 7. So what if we have 65 equals 13s, or 13 times s? Well, in this case, of course, it doesn't matter what's on the equal side, but of course a common mistake is students will divide by 65. Now, if I divide by 65, I'm not isolating any variable. I'm canceling out my answer. I still have numbers next to the s. So that won't do. So I need to remember that I need to isolate the s. In order to do that, I need to cancel out the 13. Well, whatever I do to one side, I have to do to the other. 13 divided by 13 is 1, so I'm just left with 1s equals 65 divided by 13, which gives me 5. It's okay if you say 5 equals s. You can also say s equals 5. Both are correct. But what we want to check is 65 equal to 13 times 5. And yes, it is. 13 times 5 is 65, so S equals 5, or 5 equals S. Last but not least, I want you to take a minute to pause this tutorial and try this one on your own. 12n equals 108. Okay, so let's solve this one together. So we have 12 times n equals 108. Well, I'm multiplying, so I need to do the inverse operation, which we remember the inverse of multiplication is division. So I need to divide to isolate my n. In order to do that, I need to divide by 12, which means I need to divide 108 by 12. That leaves me with n equals 9. And I need to check, is 12 times 9 108? Yes, it is. So that works out. Now I want you to write down another important rule, the multiplication property of equality. In words, multiplying each side of an equation by the same non-zero number produces an equivalent equation. In algebra, we can say x divided by a equals b, where of course a cannot equal 0. Why is that? It's because we can't divide by 0. Can translate into a times x divided by a equals a times b. Go ahead and take a minute to pause, and we'll go over some numerical examples of why this works out. Okay, so let's look at our first example. How do we solve a division equation using inverse operations? Well, we remember that fractions are fancy words for division. X over 2 means x divided by 2 equals 13. It doesn't matter if you have it as a fraction or if you want to rewrite it as a division. Both are correct. So in both cases, I want to get rid of my 2. Well, how do I do that? The inverse of division is, that's right, multiplication. So if I multiply both sides by 2, the 2's cancel out, and I'm just left with x equals 13 doubled, or 26. If I did it this way, then my 2's would cancel out here, cross-canceling, and I would still be left with just my x equals 13 times 2, or 26. How do I know that I got this answer correct? Well, I have to check. Is 26 divided by 2 equal to 13? Yes, it is, because 26 is half of 13. So I know I did this right. Let's look at another example. X divided by 4 equals 3. Well, the inverse of division, we remember, is multiplication. So if I multiply 4 to each side, I'm using the dot just so you don't get the x's confused, then the 4's cancel out, and I'm just left with x equals 3 times 4, or 12. Now I need to check if I got it right. Is 12 divided by 4 equal to 3? Yes, it is. There are 3 groups of 4 in 12. So I know x equals 12. Let's try another example. We have 3 and 4/10 is equal to x divided by 5. So I'm asking myself, what number divided by 5 is 3 and 4/10? Well, I can multiply both sides by 5. Why 5 and not 3 and 4/10? Because I need to isolate my x. So that cancels out, and I can use the distributive property, multiply 5 times 3 and get 15, 5 times 4/10 and get 2. 15 plus 2 is 17. 17 equals x. Now I need to see if this is correct. Is 3 and 4/10 equal to 17 divided by 5? It is. So my problem checks out. x equals 17. So that's using an inverse operation. So we might note that inverse operations are similar to opposites. What if you have a fraction instead of a division problem? So what if we have 4/5 of x, which would mean 4/5 times x, equals 2? Well, remember, when we divide by fractions, we have a little shortcut that works out. Instead of dividing by a fraction, we can multiply by the reciprocal. If you are struggling with reciprocals, go back to previous tutorials and make sure you're revisiting that concept. So, what is the reciprocal of 4/5 x equals 2? Why do I need to find the reciprocal of 4/5? Again, I need to isolate my x. So, my reciprocal means I'm going to flip the number. So it becomes 5/4. And remember, when we multiply a reciprocal by the number, it cancels out. Hopefully you see in this equation that 5 and 5 cancel out, 4 and 4 cross cancel. So we're just left with x equals, and I can do a little bit more cross canceling, 1, 2, which gives me 5/2. Or x equals 2 and 1/2. Now I need to see if this is right. And I'm going to actually leave it in this form because it's easier. Is 4/5 times 5/2 equal to 2? Let's look at our cross-canceling opportunities. We have 4 and 2. Both have a 2 I can factor out, so that gives me 1 and 2. And my 5s both have a 5 I can factor out, so that gives me 1. 2 times 1 is 2. 1 times 1 is 1. 2 over 1 is equal to 2. So this problem does check out. X equals 5/2 or 2.5. Let's try a few more. What if we have 4 equals 2/3 of x? Well, again, I need to isolate my x. So I'm going to multiply both sides by the reciprocal, 3/2. Because, again, I don't like dividing fractions. In this way, I can multiply by the reciprocal. So, 3/2. 2 and 4, I can factor out a 2, so that gives me 2 and 1. 3 times 2 is 6 over 1 is just 6 equals x. Now I need to see if this is indeed true. Is 4 equal to 2/3 of 6? And I shouldn't use an x for my variable here, because I don't want to confuse you, so I'll use 6. And a dot for my multiplication sign. So 6 is similar to 6 over 1. I can factor out my 3 and get 1 and 2. 2 times 2 is 4 over 1. 4 over 1 is equal to 4. So this problem also checks out. X equals 6. Let's try one more. How do I use inverse operation with mixed numbers? Well, 1.5 times y is equal to 10. Well, we remember that we can change this into something a little bit more easy, such as an improper fraction. 2 times 1 is 2, plus 1 is 5. So we have 5/2 of y equals 10. Now I have a problem that I can solve a little bit easier. So, what's my reciprocal of 5/2? 2/5. And it's 2/5 because I'm going to isolate the y. So these cross cancel out, and I'm just left with y equals, again, 2 and 1 can cross cancel, and I'm left with 4. If you didn't use the cross canceling method, you can multiply 10 times 2, which is 20, divide by 5, which is, again, 4. But when you cross cancel, you don't have to reduce. So, y equals 4, is this true? Well, I'm going to check it in my original problem with my mixed number turned into an improper fraction, just because it's easier. is 5 halves times 4 over 1 equal to 10? Well, I can see I can cross cancel. 5 times 2 is 10. 1 times 1 is 1. 10 over 1 is 10. So this problem does check out. So whenever you need to multiply by a reciprocal, make sure you change the mixed number into improper fractions first. And then you'll just use the same strategies that you used when multiplying by the previous reciprocals. One final piece, let's look at a word problem. In 1931, Ernest Swanson set a record by circling the 4 bases of a baseball diamond at an average speed of 27 feet per second. Consecutive bases are 90 feet apart. How long did it take him to circle the bases? Round to the nearest tenth. So what we need to ask ourselves is a few things. We have 4 bases. And at those 4 bases, the speed was 27 feet per second. So this problem has a few things that we need to carefully observe. Well, we know that consecutive bases are 90 feet apart, and there are 4 of them. So we first need to figure out, well, how many feet is that total? So we have 90 times 4 is equal to an average speed of 27 feet per second. So we have 27 feet per second to get to all 4 bases. How long did it take him to circle the bases round to the nearest tenth? So we need to really ask ourselves, well, 27 times what equals 90 times 4, or our bases? The question asks, how long did it take? So this is a time question. Hopefully you're recognizing this from previous tutorials. This is a distance, rate, and time problem. Our distance is our 4 bases, which are each 90 feet apart. And our rate is 27 feet per second. Remember that per is a good indicator. And our time is our unknown. So let's start by combining like terms. We have 90 times 4. Well, 9 times 4 is 36. Add the 0, 360. So we have 360 feet total at a rate of 27 times the amount of time. I have a good old-fashioned multiplication problem. 27 times what is 360? So in order to do this, I have to isolate my t. I need to divide both sides by 27. 27's cancel out, so I'm just left with t equals, and 360 divided by 27 is going to give me 13 1/3, because I'm going to get a repeating decimal of 0.33333 forever. So that would be 13 1/3 seconds. So you can say, if you chose to do the decimal version, 13 3/10 seconds equals my time. So it took him 13 3/10 seconds to circle the bases. So that's making a connection between some of our previous lessons and algebra using distance, rate, and time. Now it's your turn. I want you to carefully copy down these problems and try them on your own. So we have 3x equals 15. Then we have 14y equals 42. Remember, when we're using multiplication, what's the inverse of multiplication? Then we have z divided by 2 equals 24. Remember, fractions are just fancy words for division problems. And remember what the inverse of division is. Then we have a misprint. So let me fix this. Sorry about that. It should have been x divided by 7 equals 5. So we have x over 7 equals 5. Make sure you copy this one down correctly. And then finally we have 3/4 of something equals 9. Or in other words, 9 equals 3/4 times x. So I want you to use these strategies to try these problems on your own. Go ahead and pause the video now. In this lesson, we used inverse operations to solve multiplication and division of algebraic expressions. Now, what we also remember that we did was we multiplied by the reciprocal when we had fractions of variables. And that, of course, is because instead of dividing by a fraction, we multiply by the reciprocal. Remember to always use your inverse operations, and also remember to always isolate your variable. If you always check your answers to see if they work in your algebraic expressions, you'll know if your x or any other variable checks out. Another great job today. Remember, you can solve a one-step equation by adding, subtracting, multiplying by, or dividing by the same number on each side of equations. Great job again.